Okay. Right. Okay. All right. We'll continue from yesterday, right? So we had a problem that I'd given a problem, no, for you guys to solve. You were supposed to find the projection B S onto onto a subspace spanned by. Mhm. What is BS in this case? 2, 2, is it? What is B? 3, 1. Yeah. Okay. And did you verify it geometrically to see this is correct? No. Then how do you know this is correct? Okay. And then if you use 1, 1. Sorry, 4 by root 2, is it? Why will there be a root 2? When you use 1, 1. Really? What was the expression we had last time? If you do this, you get 2, 2? No, sorry, yes, this is correct. This is what you were supposed to apply, right? What did you get? Same, is it? 4 by root. Okay, what is it? 4 by? Okay, all right. And 4 by root 2. Yeah, okay, that's okay. Okay, you get two different answers. Which one is correct now? This is why I asked you to verify it geometrically, right? You draw this line spanned by this 1 by root 2, 1 by root 2, or 1, 1. And then you're supposed to draw 3, 1, drop a perpendicular, find where it meets, and this. Okay. I assume you guys didn't do the geometric thing, no? Okay, you should have done it. Okay. But what you will find is when you do it geometrically, what you will get is this. So there is something wrong here. Okay. The mistake is this. So if you remember how we got to this expression, we found out the cos of theta, we found out this distance, and then we said this is the length of the vector that we want. That's the orthogonal projection of B onto the subspace spanned by A. We found out this distance, and we said we simply have to then multiply this distance by A. That is true only if A is of length 1. Okay, but if A is of, for example, if A was like this, or if A was like this, would you multiply both? So let's say in the first case A was this, in the second case A was this. The subspace spanned by both these A's is just the same line. Okay, and this distance would be the same irrespective of what A is, right? But in one case you take this distance and multiply by a short vector. In the other case, you take the same length and multiply it by a longer vector, which will give you two different vectors. That's what's happened here. Okay, so it's correct. We should be multiplying A by something, but it's not just B, but the relative length of B with respect to A. That would simply be how much more do I have to stretch A to get to this point? Okay, so earlier, what did we have? How did we arrive at this? We had A transpose B. Is it right? No. Divided by A and B. Right? This is our cos theta. And then we said, well, we need to multiply to get this distance. We need to multiply this by magnitude of B or length of B. This is out, and that's what got us here. But this is not what we should be multiplying with. We should be multiplying, right? So this is okay, right? We take this. This gives you how much you need to amplify. but you have to normalize this by A. Okay. So the expression that you'll finally get is then A transpose B divided by A square. Okay. If you do this correction here, can you do the correction here and verify that this is actually, those two will come out to be the same? So instead of doing this, you simply divide it by this. Sorry? Sorry? See, you got both of these by using this approach, right? That turned out to give you two different answers, right? Which is not correct because the orthogonal projection is just this vector. So the point I'm trying to make is if you use this expression, the answer that you'll get will depend on the length of A. Here the length of A was 1. Here the length of A is not 1. Okay. To correct for that, you have to account for the starting length of A, which will result in not an expression like this, but the correct expression is this. So I'm saying you will have to divide this by the modulus A again. Or not modulus, the norm of A. Okay. Or recompute this using this expression or not this. That's what I'm saying. And what do you get if you recompute using this? Yes. So once you do this correction, you will get, this is not what you get. What you will get is 2, 2. So this is okay. Okay. See, this is one way to derive it. In the notes, there is another way. You should look at that as well because there the approach is we know that this line is perpendicular to your subspace spanned by A, and we use that to derive exactly this. Okay, so this vector Bs will simply be now this whole thing. This is a scalar, right? Multiplied. So this will be A transpose B, A transpose A. I've simply written this as A transpose A. That's all. Into A, because this is a scalar. If you scale A by this scalar, you get the orthogonal projection. Okay. Right. Now, if you go back to this expression, right? For now, let's assume A transpose A is 1. That means A is of length 1. Okay. If that is the case, then we don't have to worry about the denominator. That means our orthogonal projection is simply A transpose B. It turns out that because this is a scalar, you can move things around and you can actually write it like this. This is a scalar, so I can write 5 times the vector x and also write it like this. Both of them mean the same thing. Okay, I'm allowed to do this because this is a scalar. I won't be able to do it if well, this both of these were vectors or matrices. Because phi is a scalar, I can write it like this. That means I can move it to the side. I can write it as transpose P, and I look at, can I change my the parenthesis? It turns out you can change the parenthesis and do this. If you do that, right, what do you get for this? This will be again in this particular case 2 cross 1 vector. What will this be? What is this expression in the parenthesis? We've seen that somewhere. What is that? No, hold on. There is no a square in vectors, no? This is a vector. It's not a scalar. No, not what? No, no. Sorry. No. Inner product is row multiplied by column. This is what? Column multiplied by a row. What is that? It's the outer product. This is the outer product of A with itself. Right? And what is the shape of this entity? Is that a vector? Is that a matrix? Is that a scalar? You just apply the conditions for matrix multiplication and tell me. Right? This is of size 2 cross 1. This is of size 1 cross 2. Yes. What you get is a 2 cross 2 matrix. Okay. So it looks like you can write the orthogonal projection of B onto the subspace spanned by A like this, a scalar multiplied by A. Or another way to think about it is A transpose multiplied by B, where this is a matrix, and it's just not any matrix, it's a orthogonal projection matrix. And we'll simply write it as P with subscript S, which basically says that this is an orthogonal projection matrix onto the subspace S. And if you take that matrix and multiply it by B, you'll get. Okay. And the orthogonal projection matrix is given by this. If the length of A is for this, okay, this is the orthogonal projection matrix for projecting onto a one-dimensional subspace spanned by this vector A. Here we started. The subspace we've been talking about is a one-dimensional subspace. So the argument so far only applies to a one-dimensional subspace. The orthogonal projection matrix is given by this if the length of A is 1. If the 2 norm of A is 1. If it's not, then you have to normalize for the norm for the length of A divided by this. Or the most general expression is this: the orthogonal projection matrix onto a one-dimensional subspace spanned by this vector A. Vector A can be of any length. Okay, it cannot be 0, of course. It's a non-zero vector, and this is a general expression. If the length of A is 1, it's just the denominator disappears, becomes 1. Okay, what is the orthogonal projection matrix in this case? Where A is, let's do this, 1, 1. What will be the orthogonal projection matrix then? It'll be a 2 cross 2 matrix. You can tell me what that matrix will be. It's okay. Yeah, you do the outer product, normalize it by the denominator, and then tell me. No, why is it taking so? Yeah, that's all. 1 by 2. 1 by 2. That's all. Now, if you take this matrix and what will happen if you post multiply this by 3, 1? What do you get? you'll get 2, 2. You can verify that. Okay, so we don't have to do this anymore. Once you have this matrix, then you can just use this for projecting any vector onto the subspace spanned by A, where A is 1 by root 2, 1 by root, or 1, 1, doesn't matter. In fact, you'll get the same. You can verify if you used 1 by root 2, 1 by root 2 for computing this, you'll get the same matrix. It doesn't matter what element you choose from the subspace, what non-zero element you choose from the subspace. The projection matrix that you will, orthogonal projection matrix that you will get for projecting stuff onto this subspace will always come out to be the same matrix. Yeah. Okay. So this is for a one-dimensional subspace. You could then ask, okay, how do we now project stuff to two-dimensional subspace, maybe in 3D, right? But before we go there, okay, you have this projection matrix. Okay. What will happen if I take any arbitrary vector and I multiply it like this, the projection matrix multiplied by B, I get some vector, right? I'll get some vector like this. Okay, so let's see that we'll call it B, yes, right? That's what we've been using. What if I multiply it again? What do you think will happen? Look at it geometrically. Look at what this does geometrically. And then, of course, you do the same geometric procedure for this also. Except now you use BS instead of B. Okay. You take B, you apply PS times V. It essentially pushes this vector onto the surface, onto the subspace. And then you're taking BS and you're doing that same thing again. What will happen? Or my question, what is the orthogonal projection of BS onto the subspace S? It's not a trick question. What is it? It's the same vector. If you do this, you simply get BS again. Okay? Which basically means the orthogonal projection of a vector from the subspace is that vector itself. Because how did we compute this? Or geometrically, how did we get this vector? We took the tip of the vector B, dropped the perpendicular that intersected with the subspace S, and then we said the vector from the origin to that point of intersection is the vector. If this is already here in the subspace, the intersection of the tip of the, if you drop a perpendicular, well, the perpendicular has length 0, and that's essentially your vector itself. Okay? So this means if you have, so this also means this, right? So if PS into B gives me BS, and PS into B gives me BS, this means PS square B is equal to B. This also means this is true for projection matrices. I can't remember the name. This is probably called, there is some name for this. You can verify the notes. These are called idempotent matrices or something like that. Matrices that satisfy this property where A square is A. What about A? What about PS power N? Will this also be equal to PS? Well, yes, right? If you multiply both sides by PS, this is PS cube, this is PS square is PS, and so on and so on. Okay, so this is for orthogonal projection onto a one-dimensional subspace. What about higher dimensional subspace? Right? Let's say we have an orthonormal basis for a subspace S. Okay, and the dimension of S is, let's say, M. Okay, and S is from Rn. Of course, M is less than N. Okay. Whenever I say stuff like this, right, things should immediately pop up in your head. What does the dimension mean? What does it mean to say S is a subspace of Rn and all that? Let's say we have an orthonormal basis for S, which is basically a set of vectors. I've said the dimension of S is M. How many vectors will the orthonormal basis have? You'll have to be louder. I can't. N or M? M, is it? See? Well, the dimension of any subspace is the number of elements in its basis. This is a basis. That means it has to be M. Okay. But each of these elements itself is from Rn. Okay. All right. And we've said this is an orthonormal basis. That means Ui, Uj is 0 if I is not equal to j, and Ui, and this is equal to 1, then I equals j. Okay. If you have a basis like this, then it turns out this approach that we've talked about, building a projection matrix, applies to this as well. And all you'd have to do there is first form a matrix with the orthonormal basis vectors as columns of that matrix. So you start with a matrix called U, and you build a block row where each element of the row is your basis vector. Okay. What is the size of this? Hey, hold on. Why is this? This is a block row, but it's not 1 cross n. Each of these is a vector. N cross m. Yes, that's all. Each of these is a n vector, and there are m of these n cross n. All right. Now, the orthogonal projection matrix onto the subspace spanned by uh, uh, that orthonormal basis is simply this. And what will be the size of this matrix, shape of this matrix? U transpose. Okay. Another thing. Orthogonal projection matrices will always be square matrices, and their size will be n cross n, where n is the size of the parent vector space that contains the subspace S. Okay. When we started looking at this problem, right, we were considering a problem in R2 with the one-dimensional subspace spanned by A, right? So there n was 2. Okay, so you get a 2 cross 2 square matrix. Here, in this general case, we are considering the parent space to be Rn. S is a subspace of Rn. Okay, and so the projection matrix will be a square matrix of size n cross n. Okay. And the interesting thing is this. Let's say we have the subspace S, right? There are infinitely many bases for a subspace or a vector space. Right? You can choose any one. And there are similarly infinitely many orthonormal bases for a vector space. Right? Let's say this is one. Right? Maybe I come up with another one. V1, V2, Vm. This also spans the same subspace. And this is also orthonormal. The span of this and span of this are exactly equal, which is S. Okay, and Vi transpose Vj is 0 if I is not equal to j. If I is j, then it's 1. Now you could ask, okay, what if I now form a matrix V and I find another projection, orthogonal projection matrix like I've done here. So I form another matrix V. And this time, instead of using the U orthonormal basis, I use the V orthonormal basis. Okay. This is also size what? What is the size of this? N cross N. Now I can ask, okay, maybe I get a different projection matrix now, PS. If I do, okay, it turns out this will be exactly equal to PS. In fact, V transpose V will be equal to U transpose U. I mean, that's kind of incredible that it doesn't matter what, if as long as the subspace is fixed, it doesn't matter what orthonormal basis you choose from the subspace, you will always get the same orthogonal projection matrix. Okay. We will quickly look at an example. Let's say we're talking about R3. Let's say we have a basis, like two basis vectors like this. We're talking about a two-dimensional subspace. These are not normalized. So you can tell me what will be the corresponding. These are orthogonal. You can verify that. But how? What is the normalizing factor here? There'll be something here and something here. Once you normalize their lengths, it will form an orthonormal basis. Otherwise, it's just an orthogonal basis. And we'll call this U1 and U2. I'm essentially asking what is the normalizing factor so that the length of this vector is 1. Root 6, okay? Yeah, fine. You can now verify that this set does form an orthonormal basis for some two-dimensional subspace in R3. Okay, tell me what will be the corresponding projection matrix. You can find out and tell me. And what will be the size of the projection matrix? Yeah, 3 cross 3. Yeah, what do you get here? You have it? Okay, you're not sure? Here. You simply have to do U transpose U, right? The matrix U is simply has two columns now because M is 2, right? So your U matrix is simply 2 by root 6, 1 by root 6, 1 by root 6. And the second column is, and then you do U transpose. So your PS will simply be transpose. Okay, all right. You can do that later. Okay, we'll move on. Otherwise, we won't have time. Now, we'll go back to this idea of the four fundamental subspaces that we subspaces away. What are the four fundamental subspaces of a matrix A? Yes. Well, I won't write the names. I mean, just write the symbols. Column space of A. Okay. One space away. What is the row space? Okay. See, it turns out we won't show how, but it turns out. Okay. What is the column space? So let's say if A is a P cross Q matrix. What is the column space? A subspace of what space? RP or RQ? Yeah, it's correct. P. What about the row space? Okay. Null space? No. Q. Null space is Q. Okay. The input space. Yeah. Right. And earlier we had drawn a picture like this. Right. And we said, well, this is RP. This is RQ. And we said this is the row space. This is the column space. This is the left null space. And this is null space. And we said this gets mapped to this. If this is 0, this gets mapped to 0, and this is all left up. This is the picture we drew. Okay. It turns out we can draw a little bit a slightly better picture, because your column space and your left null space, right, are in fact related. Your row space and your null space are related. Okay. These two are subspaces of RP. Okay. And in fact, they are orthogonal complements of RP. Actually, I missed to say something yesterday. If you have two subspaces S1 and S2 that are orthogonal complements, you can actually write them like this: S1 perpendicular. Just whenever you see something like this, it means S2 is the orthogonal complement of S1. Okay. So in this case, your column space is the orthogonal complement of the left null space, and your row space is the orthogonal complement of the null space. It simply means if you add these two subspaces, you get RP. If you add these two subspaces, you get RQ. And any element from here is perpendicular to every element in here, and similarly. Okay. So, because that is true, one way to draw this picture is this is again in the notes, and this is from Gilbert Strang's lectures. This is his popular picture of depicting the four subspaces. This is RQ, this is RP. Okay. They're drawn like this. So this is the row space, this is the null space, this is the column space, this is the left null space. They're drawn like this because they're orthogonal to each other. Okay. And together they form RQ, and these two together form RP. So this is your row space. This is your null space. This is your left null space. This is your origin. This is your origin. So A maps everything to here. This maps to 0. Okay. Now, if you choose any element here, right? Any element from RQ. Okay. You can, let's say we choose an element X from RQ. We saw yesterday that if you have orthogonal complements, you can write any vector from the parent space as a sum of two, as uniquely as a sum of two components, one coming from each of the two complementary subspaces. It turns out, because these are complements, you can write X as sum of a component from the row space. That's this. Okay. You can write it as a, and this other component, which is the null space component. And so this vector, which is from the row space, will be XR. This vector, which is from the null space, will be Xn. And your X will be sum of a row space component, null space component. Okay. Anything from the null space will get mapped to 0. Okay. So if you take if you take X, right, and multiplied by A, you'll get some vector B. So this gets mapped to some element here. This is B. In fact, B is simply given by XR plus Xn. It's B. We know A times Xn is 0 because the Xn component is from the null space. So this is simply A times XR is B. So it's essentially just for any vector X that you choose from RQ, it's only the component of that vector X in the row space that gets mapped to elements in the column space. The component of the vector in the null space gets mapped to 0. Okay. All right. So with that, we will look at the last idea, at least for orthogonality for now, which is again related to the four fundamental subspaces. This is essentially to test our understanding of whether or not we've grasped the idea of the projection matrix. Okay. See, the projection matrix, right? This itself is a matrix, right? Then you can, that means you can ask about the four fundamental subspaces associated with this matrix, right? Okay. If that is the case, because this is a square matrix, the input space and output space are both Rn. Let's assume this is n cross n vector. Both the input space and the output space are n cross Rn and Rn. Okay. Okay. Let's say this is an orthogonal projection matrix onto the subspace, which is a subspace of Rn. What would be the column space of your orthogonal projection matrix? Okay. Similarly, and I can similarly ask, what do you think this would be? What is the column space? What is the definition of the column space? No. What is the definition? Okay. This is a subspace of R, in this case Rn. What elements does it have? Yes, span of the columns of the matrix A. Good. Okay. So from that definition, can we argue or can we find out what would be the column space of this, this projection matrix? Go back to that example that we drew in R2. Right? This was the subspace S. Okay. The projection matrix took any vector from R2 and projected it onto the subspace. Right? That means if you do P times PS times some vector X, what always resulted was a vector in the subspace S. That means by doing this operation, the only vectors I can produce are the vectors from S. Right? That means the column space of this matrix PS must be just this subspace. Okay, so in this case, it will simply be S. Yes, this whole subspace. This is a subspace. The column space of the projection matrix that projects to this subspace is the subspace itself, because the column space tells you what can you produce from this matrix, and all you can produce if you have the orthogonal projection matrix is this subspace. Because no matter what vector I take, right, this vector, this vector, this vector, all of them will end up as a vector here. Okay. In fact, if I have a vector that is perpendicular to this, it will essentially just be mapped to 0. Okay. So I hope that is clear. Okay. What about the null space? I mean, we can argue about these as well, but maybe talking about the null space is a little easier. What is the definition of the null space? No. Ax equal to 0 is just an expression, right? What does this mean? When you said Ax equals 0, but what is the null space? Null space is a set of vectors, right? What maps to 0? Yes, set of all x's that get mapped to 0. Now the question is, for a orthogonal projection matrix PS, can we find out what would be the null space? Well, 0 is in every null space. In fact, 0 is in every subspace. Here, think of this problem again. What vectors in R2 will get mapped to 0 if this is the subspace of your interest and you have your orthogonal projection matrix to this subspace? Well, any vector that is perpendicular to this line, if you do the orthogonal projection, it will go to 0. Right? So here, the orthogonal or the null space of your PS will simply be the subspace that is perpendicular to your original subspace, or in fact, uh, uh, the subspace that is, that is orthogonal to S, and in fact, this the orthogonal complement of S. Okay, because if you choose any vector from this orthogonal complement, uh, it'll be a vector that is perpendicular to S, and if you do the orthogonal projection, it'll get mapped to 0. Okay. Once you know these two, you know what these two are, because we know these two are orthogonal complements and we know these two are orthogonal complements. So what will be this? Well, if these two are orthogonal complements, the orthogonal complement of S is simply an orthogonal complement of S. Similarly. Okay. 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 All right. That's all I wanted to say about projection matrices. The next topic we will look at is called Gram-Schmidt orthogonalization. See, when we derived these projection matrices, right, we always started with an orthonormal basis, right, for a subspace. But what if you don't have an orthonormal basis? Okay. You remember earlier in the first example that we looked at, when we had just this vector and we were talking about computing the orthogonal projection matrix onto the subspace spanned by this vector. The first thing we had to do was, well, we could have used this expression, right? And this here took care of the fact that this is not of length 1. Okay. Or another way to address this is you simply take this vector and divide it by root 2. Right? And then use this as your A, and then you simply do A transpose. Okay? Then you get the orthogonal projection matrix. So you had to normalize the vector that you started with to get your orthogonal projection matrix. But what if you had two set of vectors? Set of two vectors which are not orthogonal. For example, let's say I have a set U1 and U2, linearly independent set, forms the basis for its span, and they are not orthogonal. That means they are not of length 1 and they are not perpendicular to each other. If you have a situation like this, then the question is, how would you derive? And you wanted an orthogonal projection matrix onto the subspace spanned by these two. It turns out there is a way to derive the expression for the orthogonal projection matrix. Or another approach is you take this, you form an orthonormal basis for the subspace spanned by these two vectors. Let's say we call them Q1 and Q2. The span of this and the span of this are exactly the same. The only difference is this set forms an orthonormal basis for the subspace, whereas this does not. Okay. If you have this, then your orthogonal projection matrix is simply, if you take Q1, Q2, you take the outer, well, basically you do U transpose, U transpose. Okay, and this will give you the orthogonal projection matrix. Okay. And the question is this: is it possible for us to derive an orthonormal basis using any arbitrary base? Okay, and one of the procedures for doing that is the Gram-Schmidt procedure. Okay, and it's quite simple and easy to understand. Okay, we will assume that we always start with a linearly independent set, right? Which of course is true if we say we are starting with a set which is a basis for a subspace, because all bases are linearly independent sets. And let's say the elements are A1, A2, AM, right? And each AI is from Rn. Okay. And we want to form an orthonormal basis using this. Okay. The way we do that is we do it step by step, starting with one vector and then the other, and so on and so forth. Okay. Let's say you have this set, right? For doing the Gram-Schmidt orthogonalization, you take the first vector. Remember, we've started with a linearly independent set. That means we know none of these vectors are of zero. None of these are zero vectors. All of them are non-zero vectors. So you take the first vector, and then you simply form the first orthonormal vector by simply taking A and dividing it by its norm. Okay. What we're trying to do here is you're starting with A1, A2, AM, and we want to end up with Q1, Q2, Qm, where this is an orthonormal basis. Okay. Getting the first vector is easy. You take A1 and you simply normalize it. Okay, you've got your Q1. Okay. The next thing you do is this. Okay, let me draw the picture here. Let's say we're talking about R2 and we want an orthonormal basis for R2. The basis we have is this. This is A1. Let's see. This is A2. This is not an orthonormal basis. Okay. So to do this procedure, the first thing we do is we take the first vector and we normalize it. Okay. You take A1 and you scale it so that it has length 1. So this is your 1. Okay. Then now to get the next vector, what we do is this. You take the next vector and you simply do orthogonal projection of the second vector onto the subspace spanned by the first vector. Okay, subspace spanned by the first vector is this. Okay, if you do the orthogonal projection of the vector A2 onto the subspace spanned by A1 or Q1, the vector you would get would be this, right? Right. So you get this vector. if you've done the orthogonal projection, we know one thing for sure. If you take the difference between these two vectors, right, between the vector a2 and its orthogonal projection onto a1, that difference vector is essentially this vector going from this from here to here. We know that that will be perpendicular to a1 or q1, right? That's essentially the idea. That means to get q2, you first compute this vector, the orthogonal projection of a2 onto a1. Okay, we'll call it maybe p1, p2 for now. P2 is simply the orthogonal projection of a2 onto a1, and we can do the orthogonal projection by computing the projection matrix. The projection matrix for this one-dimensional subspace is given by q1 transpose. If I had used a1, I would have to divide it by a1 transpose a1 because I'd have to normalize its length. But I've already done that. q1 is already of length 1, so this is fine. This is the orthogonal projection matrix. And then you take a2, that's this p2. Okay. Now we can compute this vector. All right. We'll call it R2. R2 will simply be A2 minus P2. Okay. And it will be of some length. The only thing we know for sure is R2 is perpendicular to Q1. Okay. So now all I do is I define my Q2 to be R2. That's it. Okay. Now there is a problem here. What if R2 becomes 0? Okay. It turns out it will never become 0 if this is satisfied. If you started with a linearly independent set, this R2 can never be 0. So you're okay. So this is, you can just do this. Okay. So after you do this step, the second vector Q2 will simply be a vector in this direction, but of length 1. So that will be this. Okay. So you started with A1, A2, and now you've got an orthonormal basis Q1 and Q2. This is for if you had two vectors. What if you had a third one? Let's say we were talking about R3 and you had a third vector which was like this. Again, not orthogonal to A1 and A2. Okay. You simply do the same procedure. You take A3, you orthogonally project it now not just to the one-dimensional subspace, but the two-dimensional subspace spanned by Q1 and Q2, basically to this plane, right? Now we know this line, no, which joins the tip of my vector A3 to the base or the point that intersects with the plane. We know that line is perpendicular to Q1 and Q2. The normalized vector in that direction will be my Q3. Okay. I will write down the expression. So your P3 will now be, you can verify this later. Well, let's say I form, I'll write it down. Q1 transpose A3 plus Q2 transpose A3. That's your P3. Now you compute R3 as A3 minus P3. And now your Q3 will simply be the vector R3 divided normalized R3 vector. And that will essentially be now a vector that's pointing out of this plane. And you simply continue. So if you had to compute RP, let's say you started with 4 vectors. If you wanted to compute Q4 now, you do the same thing. Orthogonally project onto a Q1, subspace spanned by Q2, subspace spanned by Q3, take the difference, normalize its length, and then you'll get Q4, and then you can continue. Okay. And you are guaranteed So if you started with m set of vectors, right, you'll have to continue this procedure m times, and then you'll get this orthonormal basis. Okay, I'm going to stop here. Okay, we will, in next week's lecture, we'll complete this next week in the first 15 minutes or so. What we will eventually see next week is this whole process of this Gram-Schmidt orthogonalization can be expressed simply like this. Okay. And this will be one of the first matrix decomposition methods that we will see in this course. And this is called the QR decomposition specifically. Okay. The columns of A are the basis vectors that you started with, which was not an orthonormal basis. Q will contain the orthonormal basis Q1 to Qm, and R is just a matrix from that you use to derive your the original basis from your orthonormal basis. Okay? And it turns out that if you have a matrix like this, if you have the QR decomposition, a lot of things become easier to do. In fact, solving Ax equals B is a lot simpler if you know the QR decomposition of A. Then solving Ax equals to B for very large matrices is actually quite simple. Yeah, so we'll do this next in the first 15 minutes next week, and then move on to the next topic. Are there any questions so far for today's topic? Okay, all right, then we'll stop here. Thanks.